Knowledge. Okay, Chemistry 3101. Last class we left off, or we finished up section 4.6, which brings us, of course, to section 4.7, which deals with conformational analysis. So something that you're going to see me do in this video is switch back and forth between my slides and my camera. So just be patient because it takes a couple of seconds to switch back and forth. But if we look at the molecule ethane, right, a very simple molecule in last class, we said, okay, well, you have ethane like this, and then you could draw it in 3 dimensions where you have, a hydrogen going back behind the screen and one coming out like this. Then you do the same thing on this carbon like that, right? And then you have a hydrogen here. But if you were to look down the carbon-carbon bond, and I'll just move this over a little bit. So if you were to take your eyeball, and here's my drawing of a human eyeball, just need a blue pen here. There's a human eyeball, there are the eyelashes, right? And if you were to look down this carbon-carbon bond and draw the Newman projection, this is what you would see, the way I have that ethane molecule drawn. And you see that the angle between the atoms on the 2 carbons, the adjacent carbons, we call that the dihedral angle sometimes, and we call it the torsional angle sometimes. It's 60 degrees in the way that this molecule is drawn. And if you're wondering, well, isn't there free rotation around this carbon-carbon bond? Yes, absolutely there is. So we can change that angle, and we're going to talk about that. But the way that the molecule is right now and the way that it is right here, you see that I've distanced the hydrogens the maximum amount that they can be from each other. So the biggest dihedral or torsional angle that we can have is 60 degrees, okay? 60 degrees, think about it, 360 divided by 6, and you end up with 60 degrees. Anyhow, another thing you'll notice about me, just the way I lecture personally, is I don't use the term torsional angle a whole lot. I was raised, from a baby when I started learning organic chemistry with the word or the term dihedral angle. It's what I grew up with. So I will probably say that most of the time. Dihedral angle. We're going to talk about those again quite a bit. Now, what's interesting again is if you rotate that carbon-carbon bond, you can have a conformation. So these are, when we rotate that bond, what we get are different conformations. You can have a conformation where all the hydrogens are blocking each other. Now, it's pretty difficult to draw something on paper where you show every hydrogen, exactly blocking, on top of another one. So we draw it, slightly askew like this. And the difference between the conformation where the dihedral angle was 60 degrees, okay, versus this one here where it's actually 0 degrees. I know it does. You're like, well, there's a little angle here. It means there's no angle. Again, it's hard to represent. But the difference, or the names of these, the one where we have the largest dihedral angle, we call that the staggered conformation. And so you need to know what a staggered conformation is. And when they're blocking each other, I think it's a little more intuitive. We call that the eclipsed conformation. So the eclipsed conformation and the staggered conformation. And I don't think that it's much of a stretch for you to understand that the difference in energy between these is that the staggered conformation is going to be lower in energy than the eclipsed conformation, right? Just think about it. Everything here is distance, right? Remember VSEPR theory, valence shell electron pair repulsion theory? What was the whole idea? That bonds, right? Atoms wanted to get as far away from each other as possible. And we see the same thing here, right? Now, in this conformation, you see that we have all those bonds getting closer to each other. And so it creates what we call torsional strain. So the difference in energy between these conformations, we call it torsional strain. And here, the difference in energy is 12 kilojoules per mole. In fact, if you read the textbook, he says something like, if you have a sample of ethane at room temperature, and ethane is just a gas at room temperature, it's a very small molecule. If you have a sample of ethane at room temperature, then 99% of the molecules are in the staggered conformation. Why? Because they're so much lower in energy. And so if we look at a plot of potential energy on this y-axis versus the dihedral angle, right? If we start with the angle of 0 degrees, and we're just looking at the 2 protons that are highlighted in red. Yes, I know there's 6 protons, but we're going to focus on the ones highlighted in red. You see that if you go from the 2 highlighted in red and then you rotate the bond so that you have a dihedral angle of 60 degrees, then everything is spread as far apart as possible, and we're going to drop in potential energy by what? That 12 kilojoules per mole. If we crank it another 60 degrees, we get to 120 degrees, okay? And again, that's the angle between these two. But now we're in another eclipsed conformation, and we're at that energy maximum, right? If we dip down again to 180 degrees, well, all we've done is rotated the molecule another 60 degrees, and now you see that these two hydrogens are as far apart as possible, but you see that everything is completely staggered, right? And we could do the same treatment going backwards, right? If we, oops, let me go back. Where's my green pen? It was somewhere here. There we go. If we go backwards from here, right, if we rotate the molecule 60 degrees, or rotate the bond, I should say, 60 degrees, we have that dihedral angle of 60. We're at an energy maximum. Why? Or minimum, rather, because everything is staggered. So what you notice here, and I'm not going to do the whole thing, but you notice that everything here is staggered, okay? And you notice that the energy of all the staggered conformations is degenerate. What does degenerate mean, right? It doesn't mean that you should, you've committed a crime or something like that. It's not that use of the word degenerate. Degenerate means same energy, okay? Same energy. If you remember in General Chemistry 1, you talked about degenerate orbitals, like a 2p orbital. You have a 2px, 2py, 2pz, and they're all degenerate, right? So you've seen that before. But you notice that all of the staggered conformations in ethane, we're particularly talking about ethane on this slide, you notice that they are all equal in energy. You also notice that all of the eclipsed conformations of ethane are all degenerate, right? These are all of the eclipsed conformations, and they're all degenerate as well. And what's the difference in energy? It's 12 kilojoules per mole. Well, there we go. So let me just go over the camera here for a second, and I'm just going to show you. And I'm sure that you're all following me, but I want to do a little demo here with my model kit to show you the conformational analysis of ethane. So let me go over to my camera here. Go. All right. So here is a model of ethane. This is CH3. These models are called Feezer models. And here's the model of CH3. And if you look down, and I know that this is silver and this is black, but they still represent carbon-hydrogen bonds. You have to imagine they're all identical. But if you look down the carbon-carbon bond axis, you see that all the dihedral angles here are 60 degrees. So this is a staggered conformation. If we rotate it like this, then we get an eclipsed conformation. Okay, we have an eclipsed conformation. If you rotate it another 60 degrees, you have another staggered conformation. If you rotate it another 60 degrees, you have an eclipsed conformation. So in terms of the relative energy, you go from staggered to eclipsed, higher in energy, to lower in energy, right? I'm doing my best here to demonstrate. But anyhow, hopefully you get the idea. Give me a thumbs up if you follow me on just the idea of what's going on here with the conformational analysis of ethane. It's important that we start out that you understand, what's going on before we look at molecules that are a little more complex, because I'm just going to tell you that right now we've looked at ethane, which again is CH3, right? 2 carbons. Next, we're going to move on to propane, and then after that, we're going to look at butane, and butane is a little more complicated, okay? But see if you can follow me here with propane. So everybody here should know what propane is. Propane is nothing more than, right, 3 carbons like this. There's only one way to arrange the atoms, right? There's only one isomer that you can have for propane. And it says the analysis of the torsional strain of propane is very close to that of ethane. Right, we have all of these staggered conformations, staggered, okay, and up here we have all of the eclipsed conformations, eclipsed, and you notice, again, just like ethane, that all of the staggered conformations are degenerate, right? They're all equal in energy. You see they have the same energy level, or same amount of energy, or amount of potential energy, I should say. You see that all of the eclipsed conformations are degenerate, right? They're all equal in energy. And the difference in energy between the two, the staggered and eclipsed conformations, is 14 kilojoules per mole. Now, our book goes into quite a lengthy treatment as to, the energy cost for this interaction and the energy cost for this interaction. If we go back here to the ethane molecule, you notice that the difference in energy between staggered and eclipsed was 12 kilojoules per mole. right? This is 12 kilojoules per mole higher in energy. Well, there's one, two, three of those hydrogen-hydrogen interactions. So if you take 12 divided by 3, what do you get? You get that the cost of each one of these is 4 kilojoules per mole. So if I go over to my propane molecule, if this costs 4 kilojoules per mole and this costs 4 kilojoules per mole, but my total is 14, well, what's 14 subtract, a total of 4 plus 4? So 14 subtract 8, what are you left over with, right? 14 subtract 8, you're going to be left over with 6 kilojoules per mole. So that barrier for rotation, or that barrier to rotation rather, for propane, again, 14 kilojoules per mole. It's 2 kilojoules mole for ethane. And if we actually try to evaluate the torsional strain for every eclipsed hydrogen-hydrogen, I showed you how each one is worth 4 kilojoules per mole. So then you subtract both of those. So you have one here and you have one here. You subtract it from the total of 14 and you get 8. So the cost of the torsional strain, from the hydrogen and the methyl group, that eclipsing interaction costs 6 kilojoules per mole. You know what? I've taught this class a long time, and I've written a lot of quizzes where I've asked a lot of questions about organic chemistry and about conformational analysis. I don't think I've ever really gotten into the nitty-gritty on the numbers, right? Because in our textbook, there's a table where he shows you the cost of every bit of strain. And I've never really gotten hardcore into the numbers. What I want my students to know is this. I want them to understand, and when I mean them, I mean you, okay? I want you to know that the cost of energy for the interaction between two hydrogens would be less, right, than the cost of energy for the interaction between a hydrogen and a methyl. Why? Because a methyl's bigger, right? So it's going to block, more. It's going to be a higher energy cost with that, okay? I'm not going to be asking you like, oh, this is 4, this is 6. How much is this? I'm not going to be asking you to do a bunch of math on that. All right. But if I go back to my camera here just for a sec, okay, I'd be remiss if we didn't quickly look at the conformational analysis of propane, which isn't that exciting after you've seen the conformational analysis of ethane because it's so close, right? But here's a propane molecule, nothing fancy, right? And I could either look at the carbon-carbon bond and put the methyl group in the front or put the methyl group in the back. It doesn't matter. But I'm going to put it in the front because it's a little easier for me to manipulate like that. But you see how here is a staggered conformation. If I rotate that by 60 degrees like that, I get an eclipsed conformation. And you see the torsional strain between this carbon-hydrogen bond and this methyl group that's out here, right? The carbon bound to this methyl. And you can see how that's going to be a higher energy cost than just these little 2 hydrogens here or these 2 hydrogens here, right? I rotate it another 60 degrees like that. What do I have? I have another staggered conformation, but you can see that it's identical to the one that we started out with, right? So it has the exact same energy cost, right? If I rotate it another 60 degrees, I have another eclipsed conformation, but again, you can see it's identical to the one that we looked at before. So you can see how all of the staggered conformations are degenerate, right? They're all equal in energy, and I could put it over here like that. It doesn't matter. They're all equal in energy. Oops. There you go. That's a little prettier. And if we draw or if we twist it so that it has eclipsed, okay, you can see that they're all degenerate in energy. Okay, so not really that crazy. You know what? I have my camera on. Let's take a look at a butane molecule quickly before we look at the conformational analysis on paper. Here's my butane molecule. Remember that the reason we draw hydrocarbons once we have 4 carbons and more, the reason we draw them as zigzags like this, like a zigzag on Charlie Brown's shirt, right, is because this is the lowest energy conformation, right? We know there's free rotation around this carbon-carbon bond, but and you could draw butane that way. There's nothing, it's still butane, right? You could draw it, go, you can do that, but this is higher in energy, right? So if we look at the conformational analysis of butane, check this out, okay? Let's just focus on staggered conformations first. Here's the first staggered conformation. You see how the 2 methyl groups are as far away from each other as possible? Look what happens when we go to the next staggered conformation. It is not the same, is it, as the last one? Because now these 2 methyl groups have a dihedral angle of 60 degrees. Now they're close to each other. We call that a gauche interaction. Look at the next staggered conformation. It's just like the last one. You see how the two methyl groups are next to each other? They have that dihedral angle of 60 degrees. We call that a gauche conformation. Could anybody tell me what you call this conformation? Did anybody read enough of the book to tell me what this conformation is called when the two methyls are as far apart from each other as possible? I'll just hold this here like somebody, you know, on The Price is Right or something until I'll see if I can see my chat here. Could anybody tell me what this conformation is called? Or this interact? Yeah, this conformation. So I had the two gauche conformations, and there's a word for this one. Anyhow, I can't wait any longer. I can't hold this up any longer. It's called the anti-conformation. So anti is when the methyl groups are as far apart from each other as possible. And when you have a staggered conformation where the methyl groups have that dihedral angle of 60 degrees, that's called gauche. So we have two gauche conformations like this. There's a gauche. Go back. There's the other gauche conformation. And there's the anti-conformation. You can imagine that the anti-conformation is lower in energy, right? Because you don't have the steric interactions between the two methyl groups like you do when they're in either of these gauche conformations like that. Okay? Give me a thumbs up if you follow me on the rationale there. Anybody with me on the rationale of butane? Butane is quite a bit different than the ethane molecule. Okay, cool. Oh, I see that somebody typed it in. Sorry, I missed that. Allison and Jonathan, I see that you typed it in there now. I told you my MacBook's acting up. All right, so we're still recording. Good. Well, let's go back here and let's get into that butane molecule. So what we saw, and I just focused on the staggered conformations with you just now. So all we did was analyze these conformations right here, and we saw that there's a difference in energy, right? Or there should be a difference in energy because these two conformations, right, the two methyl groups are close to each other. Whereas this conformation and this conformation, which are identical, you see that the methyl groups are as far apart from each other as possible. And you can see that manifested in the difference in potential energy. Look at this. I'm going to use the green highlighter. Here's the conformation where the two methyl groups are as far apart from each other as possible. Again, we call that the anti-conformation. Okay, so we could even write that in here. This is anti-conformation, and this is the same thing. Okay, this is anti-conformation. These two here, look, I'll use the blue highlighter. I don't use the blue highlighter a lot, but you see how these two conformations are staggered, but they're higher in energy than the ones that are in green, aren't they? Right, they're higher in energy by 3.8 kilojoules per mole, and that's because you have these gauche interactions. So this is called a gauche interaction, the fact that the methyl groups are close to each other and they're causing some strain. Now, we didn't talk about the eclipsed conformations, but the same rationale that we just used would apply for the eclipsed conformations, which are all up here. There's two types of eclipsed conformations for butane, unlike propane and ethane, which only had one type of eclipsed and staggered conformations, right? But here there's two types. There's the ones where the methyl groups are being blocked or being eclipsed with a hydrogen, and then there's one that's different where you have the two methyl groups eclipsing each other. Okay, and you see that that's higher in energy. I'll use the yellow highlighter. You see that this is higher in energy, and I'll use the red highlighter for these ones. It's higher in energy than these other eclipsed conformations. Okay, and again, there's an energy cost associated with those two methyl groups aligning. Well, let's get back into those staggered conformations. So the difference in energy of the staggered conformations that we analyzed, the gauche and the anti, is 3.8 kilojoules per mole. So terms that you need to know. It says here when the methyl groups are gauche to one another, here we have gauche and gauche, right? There is a steric strain and a higher energy conformation, right? You could we draw lines like this sometimes in chemistry to represent they're crowding each other, right? But you can either way, you can see the green circles that highlight the methyl groups that they're really close to each other. That's a lot of electron cloud, a lot of electron density next to each other. They don't like that. Whereas in the anti-conformation, right, the two methyl groups have a dihedral angle of 180 degrees. They're as far apart away from each other as possible, and so they are going to be lower in energy. You do not need to memorize table 4.6, okay? So no need to memorize. Now, I said that carefully. You don't have to memorize table 4.6, but, okay, you should know the concept or know the concepts that are on there. Okay, so what does that mean? If you're like, what does it mean? What's the difference between memorize it and know the concepts? Well, memorizing it would be, I ask you to memorize every value, every numerical value on there. It's not that we're interested in. I want you to look at the table and look at the trend. As long as you understand the trend, and if you understood most of what I'm talking about this morning, you already understand most of the trend, okay? Or probably all of the trend. I just don't want to misspeak and say, you know everything, Nobody knows everything about organic chemistry except R.B. Woodward. He is dead, but he knew everything about organic chemistry. If you don't believe me, you can look him up. It's Robert Woodward. Anyhow, only person in history that knew everything about organic chemistry. All right, well, let's move on from there and let's talk about cycloalkanes. Right? If you go back to, the beginning of this chapter, right, we said we're going to talk about alkanes and cycloalkanes, and we started talking about nomenclature of cycloalkanes. We even practiced naming some cycloalkanes, which was really fun. We talked about this molecule, which is cyclopropane, and then we went to a cyclobutane, and then cyclopentane, and then cyclohexane, and then I even drew a cycloheptane for you, this one here. I'm not good at drawing heptagons. And then a cyclooctane. Well, what's interesting about these is that if you look at the carbons in all of these cycloalkanes, every carbon is sp3 hybridized, right? Well, what's the bond angle of or the preferred bond angle, I should say, of an sp3 hybridized carbon? You guys know that, right? You know that from general chemistry, that the tetrahedral, right? When you have an sp3 hybridization, bond angle is 109.5 degrees. Well, what's interesting about this is that when chemists analyzed the stability of cycloalkanes, and there's some interesting history that's mentioned in our textbook, they thought that small cycloalkanes like cyclopropane and cyclobutane, they thought they didn't even exist. Okay, they said these things are just way too unstable because the bond angles that are shown on this slide are just so small, right? 60 degrees, 90 degrees. And what they postulated is that the most stable of all the cycloalkanes should be cyclopentane. Why? Because the bond angle here is the closest to 109.5 degrees. Okay. Now, there's a serious problem with this. Okay. So the serious problem is that what they were doing wrong is that they were assuming that these cycloalkanes were planar, and they are not planar, right? We know that molecules are three-dimensional, right? So if the ring was flat, all of the carbon-carbon bonds would have eclipsing rotamers. So you know how we looked at eclipsing hydrogens and methyl groups? Anyhow, if these were planar, everything would be eclipsed. Okay, so everything would be super high energy, but we know that we alleviate that torsional strain by adopting a three-dimensional shape. And so what happens is if you actually look at the stability of all of the cycloalkanes here, much to the surprise of the scientists who thought that these were planar, they found that cyclohexane was actually the most stable of all of them. And if you're wondering, how did they evaluate the relative stability of all of these cycloalkanes and more? Well, what they did is they basically just burned them, okay? So they burned them and then they measured the heat of combustion. Now, if you were to go from cyclopropane to cyclobutane to cyclopentane, if you were to just compare the heat of combustion of the molecule, well, that's not really fair because they have different numbers of carbons, right? You go from 3 to 4 to 5 to 6, so on and so forth. So what they did, or what you do, is you compare the heat of combustion and then you divide it by the number of methylene groups that there are in the molecule. Okay, so then if you plot that, here are the numbers right here, but here's a plot which I think is a lot easier to look at. You look at the heat of combustion per methylene in a cycloalkane, you notice that cyclohexane releases much less energy than the rest. Okay, and if you follow the trend here, and we're not going to look at cyclododecane really, but you see that you think it just keeps increasing, but it drops again here, which is kind of interesting. But we're going to focus most of our time on cyclohexane, right? This is cyclohexane. Why? Because it has the lowest heat of combustion per methylene group. What does that mean? It's the most stable. And the reason why, when we look at the model of cyclohexane, it's the only cycloalkane where every carbon is perfectly tetrahedral, okay? Out of all the ones that are shown on this slide here, okay? And again, so this is incorrect, okay? These are just historical values, or these are actually the values if they were planars, I should say. So what you actually find is that every carbon in here is perfectly tetrahedral. So that's kind of interesting. Well, if we look at cyclobutane, and down here I noticed that I put a picture of cyclopropane. So let me just address cyclopropane first. I don't know why I should have titled this slide cyclobutane and cyclopropane, since I snuck this cyclopropane down here. So cyclopropane, I'll tell you what, you guys, I have my model kit out here, and I'm not even going to make a model of cyclopropane, which is this molecule, and I'm not going to make a model of cyclobutane, which is this molecule over here, butane. Why would I not make a model of either of those to show you? Because if I did, I'd break my model kit. Okay, it would snap the bonds, and my bonds in the Feezer models are not they're not bendable. Okay, they're not bendy, so it would just end up breaking them. Okay, but anyhow, if you look at cyclopropane, okay, so we'll start there. Well, what's the hybridization of every carbon? It's sp3 hybridized. So this, all of these blue lobes that you see here, these are just sp3 hybrid orbitals, right? That's sp3, that's sp3. But what happens is, in order for there to be an overlap of those orbitals, they actually have to kind of bend like this. You see how they're not straight, right? They're showing that they're kind of coming towards each other at an angle. And what that does is it causes significant ring strain. And so cyclopropane is a very relatively unstable molecule and is very prone to ring opening. And in fact, in organic chemistry too, we do a whole chapter where we look at three-membered rings. And not the entire chapter, but a big part of the chapter is devoted to three-membered rings and how prone they are to ring opening because of that bond strain. Now, if you look at cyclobutane, and again, I'm not going to make a model of that, but the angle strain, it's got bond angles of 88 degrees, and it has slight torsional strain because the adjacent carbon-hydrogen bonds are not completely eclipsed and they're not completely staggered. So it adopts this kind of puckered conformation, and it's represented here. Basically, it kind of bends in a little bit. And the reason that it bends like this a little bit is to try to alleviate as much torsional strain as it possibly can. So once we move over to 5 carbons, that I can do with my model. I can make a model of cyclopentane, and I can show you something cool about that in a second. But let's move on from there to cyclopentane. So cyclopentane is less stable than cyclohexane, which I told you is the most stable of all, but it's not that much less stable. All the bond angles are pretty close to 109.5 degrees. It's got some slight torsional strain, and so it adopts this envelope conformation. Now, if you're like that, I'm sorry, Mr. Dion, but I've sent my friend a Christmas card or a birthday card, and that doesn't look like an envelope to me. Well, let me show you what it means by an envelope. So let me go back to my camera here and see if I can shed some light on the whole concept of the envelope conformation. So here's the cyclopentane. If you think about it, or if you just view it being planar, it just looks like it's flat as a pancake like that. But what happens is it's not flat. It adopts this kind of conformation like this. So you see how these 4 carbons, 1, 2, 3, 4, are in a plane. And then you have this one kind of bent up like that. You can kind of think about it as an envelope. Like here's the part that you have the card in to your friend, and then here's the flap that you're going to fold over. And that's what we mean by an envelope conformation. What's cool is if you take the carbon that's pointing up in the envelope, and it could be any one of them. It could be this one. I can move it around. I can make it this one. I can make it this one. It doesn't matter. But if you look down the carbon-carbon bond of the envelope, look at that. It's almost completely staggered. I can even push it up there a little bit. And you see that it's almost completely staggered. I'm talking about this carbon-carbon bond right here, this one. Okay? But if you look at the other ones, look at this. It's eclipsed. Look at this one. This one is eclipsed too, or almost eclipsed. So the book doesn't talk about this, but what it actually does is it keeps moving, right? It's flexible, and so it's always like moving around like this. So every carbon is getting a chance to be, the pointy part of the envelope. And the fact that it can move like that at room temperature allows each carbon to have partially, to be partially staggered and relieved a lot of that ring strain. And so that's why cyclopentane is actually a pretty stable molecule. Okay, you can, do reactions of cyclopentanes and things. So that's kind of interesting. All right, let me get back to my slides here. So cyclopentane, but again, as I told you, the large focus of the remainder of this chapter is going to be about cyclopropane, cyclobutane, or cyclopentane. What's it going to be about? It's going to be about cyclohexane. Okay, cyclohexane can adopt a whole holy host of conformations that you see here. You got all these different ones. You got a chair, a half chair, a boat, a twist boat, right? Well, you know, students sometimes will say, well, how in the hell is this a chair? That doesn't look like a chair to me. Well, this is a representation of it being, you know, kind of just moved a little bit so that it looks like a chair. So this and this, you know, what the person is sitting on here, you can see how that looks like a chair, right? You put your head up here, put your tuchus there, right? Your arms and your legs like that. So that's what it means by a chair. If, you know, every once in a while I get somebody who's like, that doesn't look like a chair. Okay, well, that's what they mean, a chair. And the boat, we don't even look at a boat a whole lot, but a boat is a lot more intuitive, isn't it? That looks a lot more like a boat than the chair looks like a chair. But anyhow, in our class, in Chemistry 3101, we're going to focus 98% of the time on the chair. We're going to talk about the boat briefly. And the whole concept of a half chair and a twist boat, you don't really have to concern yourself with those a whole lot, but I am going to demonstrate them for you just so you see where they're coming from. And you see that there's a difference in potential energy for all of these different conformations. Okay, when we go from the chair, then you go to the half chair, which is the highest energy conformation. Then you can have a boat, which is, you know, intermediate between the half chair and the chair. And the twist boat is actually a way that you can manipulate the boat to alleviate some of the torsional strain in that molecule. So let me show you. And if you're wondering, you know, Mr. Dion, what is the difference between this and this? It looks just like they're reflections of one another, right? If you had a mirror there, they're reflections. Well, actually, these are different conformations. Okay, so we're actually rotating carbon-carbon bonds when we get from here to here. We're not breaking carbon bonds. We're rotating carbon-carbon bonds. So let me show you what I mean. And I'll grab my handy dandy model kit. Just give me a seckaroo here. Some stuff presenting. So I'll take my cyclopentane that we started with, and I'm going to throw a carbon in there. So let's grab a carbon. So I put another carbon in the ring. So this is hexane. I don't know if there's enough room, the camera, for me to show you the model of hexane. But there's hexane. You see how it's zigzag, like Charlie Brown's shirt, right? Up, down, up, down, up, down, right? So if we take that and we make a ring like that, we end up with a cyclohexane molecule. So don't focus on the atoms that are pointing up, like focus on the ones in the ring, right? You see how that's a 6-membered ring that I'm holding up there? Well, if you hold it like this, you can see the chair. Okay, so here's one of the chairs, one chair conformation. Hopefully everybody can see the chair conformation in there. I'm holding it the best I can to see the chair. Now watch, I'm not going to flip it like a pancake. Here's my chair. Watch, now I'm just going to rotate all the carbon-carbon bonds, and you end up with the other chair. Okay, notice how this part of the chair is pointing up, so you'd be sitting, look, with your feet dangling this way in the chair. Right now, I just rotated the bonds, okay, and now your feet would be dangling down here. So when you hear me talk about flipping the molecule, I'm not talking about doing this like a pancake, right? You take a spatula and you flip it over. No, when we talk about ring flip in organic chemistry, what we're talking about is rotating the bonds. Look, when I'm doing this, because I do it quick, right? Okay, what I'm actually doing, watch carefully, is that I'm actually rotating bonds. Okay, it just happens really quickly when you flip it like that. So there you go. So there's the chair. Here is the half chair. And the reason the half chair is so highly strained is you can see there's a bunch of eclipsed hydrogens. These are eclipsed. These are eclipsed. These are eclipsed. Anyhow, that's neither here nor there. Then you have the boat. The boat is pretty darn cool. Okay, you can see the boat like this. But the problem with the boat is that we do have what are called flagpole interactions here. These two hydrogens are blocking each other, and we'll talk about that a little bit. And then the twist boat, just to alleviate the strain from these hydrogens all being eclipsed, right, is you just take it and you twist it like that. And I know it's not easy to see, but you just twist it a little bit like that, and it will alleviate some of that strain. So look, here's the boat, okay, perfectly symmetrical. All you do is you twist it a little bit like that, and you get a twist boat. Okay, like that. There's the twist boat. So we go from the chair to the half chair to the twist boat like that, and then you have the boat, and then you just twist it back, half chair, and poof, the other one like that. All right, there you go. So there's a chair, as they say in Boston, the chair. All right, you got to know the chair. And again, you know, I always have students who love to share memes in organic chemistry with me, and I don't know if you've ever seen this one, but there's one where it's like things I learned in organic chemistry, how to draw hexagons, right? And the reason why is because cyclohexane is such an important molecule. I even read a blog post one time that somebody who was doing an arts degree came to an organic chemistry lecture just to see what was going on, and he's like, "Professor is just drawing shapes, you know, I don't understand. Professor won't stop drawing shapes. I can't figure out what these mean." Anyhow, so here is cyclohexane drawn, you know, just in 2D, but when we draw the chair, and we're going to show you how to draw a chair today, you can either draw the chair in this conformation where you have it going like this, okay, and there's one of my chairs, so that's this conformation, and then we can also draw the chair. If we flip it, it'll look like this, and that's the best I can do at the moment. Okay, there you go. So again, the reason why cyclohexane is such a special molecule in organic chemistry is because it's the only cycloalkane that has no ring strain in the chair conformation, right? Every bond angle is 109.5 degrees. Something I didn't show you, but if you look down any carbon-carbon bond axis, so right, everybody's got, you know, if you take two eyes, right, and you look down these two carbon-carbon bonds, this carbon-carbon bond and this carbon-carbon bond, this is what you would see. But that's neither here nor there. The whole idea is if you were to look down both of those bonds simultaneously, this is a Newman projection of cyclohexane, and look at it. I don't see a single gauche interaction in there, right? There's no torsional strain whatsoever. Everything is completely staggered, right? Everything is as far away from everything else as possible. So there you go. Cyclohexane has no ring strain, and that is why it is such a special molecule. So drawing chair conformations. Now, I've taught this class long enough to know that you can use Skill Builder 4.9 to help you learn how to draw chair conformations, okay? So this is the David Klein 5-step, unpatented, you know, patent pending method of drawing chair conformations. There is nothing wrong with this method. I have many students who have learned how to draw cyclohexane chairs using this method, the big wide V, and then you draw lines, you know, following these steps. I mean, you can use this technique. I just kind of learned how to do it, you know, just by looking at them long enough, you know, you just kind of get the feel for it, what the angles should look like, something like this, and that's not even all that great. I could probably spruce that up a little bit. There we go. Like this. But one thing that you notice is that it's made up of a set of 3 parallel lines, right? If you notice, this bond and this bond are parallel to each other, right? This bond and this bond are parallel to each other, and then this bond and this bond are supposed to be parallel to each other. They're not perfectly parallel, but you can see they are in here, okay? So I'm going to leave it with you like this. You can practice using this method. Now, I'm going to leave it up to you. If you want to go on the internet and suss out other ways of drawing chair conformations, by all means do that. If you have no place to go, you know, you could just start with this. Now, I always have somebody who asks me about the templates, right? Because you can probably buy them on Amazon or wherever. You can buy these templates that help you draw chairs. You just put it on top of a page and I could, you know, draw a chair in 10 seconds, right? Or sorry, what do I mean? 2 seconds more like it, you know, and it looks exactly like this. What I would say is this. For practicing, there's nothing wrong with using that. Okay, if you're practicing drawing chairs and you just want to get to the heart of the problem, you know, of the question that's being asked, yes, you can use those templates. I think that drawing a chair is a valuable skill for anybody who studies organic chemistry. I don't see why you would take a whole semester of organic chemistry and not want to learn how to draw, one of the most important things in the class, okay? But again, when you're practicing using the templates, I say go for it. However, I think it's wise for you to be able to draw a chair. Now, normally, if we were not in the pandemic and the class wasn't remote, if we were in, you know, Centennial Hall right now, all of us together in a room, and I was giving you paper quizzes, I would definitely ask you a question where I get you to draw a chair, okay? And I'd get you to draw 2 conformations. I wouldn't like inundate you with questions about it, but I would ask you at least once to draw a chair in the class. You know, you've enrolled in organic chemistry, you should know how to draw a chair. So that's kind of my thoughts on that. Okay, so it would be practice, practice, practice. Of course, you're not going to be asked to draw. I'm not going to ask you to draw a chair in your quiz. I'll just tell you that flat out. Why? Because your next quiz is going to be a multiple choice quiz. But anyhow, if you draw the chair correctly, it should contain 3 sets of parallel lines, as I showed you. Now, each carbon on the ring has 2 substituents, right? Why? Because if you look at this is a CH2, so there's 2 hydrogens. This is a CH2, right? So on and so forth. So we have 6 methylenes in cyclohexane, so there's 2 substituents on every carbon. But there's 2 positions. There's what we call an axial position and an equatorial position. So every carbon has an axial position and every carbon has an equatorial position. So let me go over to a blank document here just for a second. Let's see here. There we go. So if I have a blank document like this, and if I draw a chair, okay, and I'm going to try to draw one the best I can. I do the best that I can. All right, so draw something that looks like this. Okay, close enough. Okay, it's not the perfect chair, but it'll do. Right, that's my skill level with drawing chairs. And I worked in a carbohydrate lab for a couple of years, so we were always doing, drawing chairs, and then we draw this, to draw glucose molecules or whatever. Anyhow, that's neither here nor there. Let's delete that. But on every carbon, you've got 2 positions, the axial and equatorial. Now, how do you tell which is which? Follow me on this. If we just focus on this carbon right here, so I'm going to draw carbon, okay? Take the bond going towards the carbon like this and the other bond going towards the carbon, okay? Where are those pointing? Are they pointing, do they look like they're going up or down? And it's not a trick. Are those arrows that I have with the arrowhead, are they pointing up or down? Okay, they're pointing up, aren't they? So what that means is nothing more than this. It means that one of the groups or one of the protons is going to be going straight up like this, okay? Straight up. So that means that what we call the axial position will be going up, okay? Let's try the same treatment, and you can use this all the time. Oops, I didn't mean to do that. Let's pick another carbon. We'll pick one at random. Let's pick this carbon right, oops. Keep erasing everything. Let's pick this carbon here, okay? If you draw the bond towards it, this one's going up and this one's going up. So it means that the axial hydrogen is going to be going straight up like this, okay? What about this carbon here? This bond is pointing down and this bond is pointing down. So it means that the axial position is going to be going straight down like this. Same thing, and I'm kind of running out of colors here, aren't I? But if you look at this bond is going down, this bond is going down. So that means that the axial position, the one that's either going straight up or straight down, on this one is going to be going down. Here you see it's going up, and here it's going down. Give me a thumbs up if you follow me on axial positions. That you look at the 2 bonds going towards that atom, that carbon, and if they're pointing up, then the axial position goes up. If they're pointing down, right, I'll show you one last time. I'll use my yellow pencil here. This bond is going down. This one is going down. So the axial position is pointing down. Okay, so those are axial positions. The next positions are called equatorial. So I'll draw them in using the yellow pencil. Okay, so here's an equatorial position. Here's an equatorial position. Here's an equatorial position right here. Okay, here's an equatorial position right here. Here's an equatorial position like this, and here's an equatorial position like that. And if you're like, what? How did you know how to draw those in? They're a little more complicated, aren't they? Okay, so let me start by redrawing the chair. I'm going to draw a new chair here, and we're going to talk about equatorial positions. So let me do my best at drawing a chair. That's not a very good chair. See, if at first you don't succeed, just try again. Right? Okay, this is going to have to do for now. Okay, so there's another chair. So we had all the axial positions. I'll draw them in quickly. We'll put a hydrogen on each one. Here we go. Here we go. Here we go. Notice that there's 3 hydrogens that are going up. I'll highlight them in yellow. Right? There's 3 axial hydrogens that are pointing up, and then there's 3 axial hydrogens that are pointing down. Look, and you notice that they alternate. Look, it goes up, down, up, down, up, and down. So they alternate, the axial ones. Well, what you're going to see is that the equatorial ones do the exact same thing. So I'm going to use the blue pen to represent equatorial. So here's what you do. Let's focus on this carbon. How do I know how to draw the angle going down like this? So you go one bond and then the second bond. You go one bond here and then the second bond. And this bond should be parallel to the other two bonds that I have in blue circles. Okay, so you always go one bond away and you look for the parallel line. So look, this carbon here, also in blue. The same too. You have this parallel line and then this line. So that means that this hydrogen is going to be pointing up like this. Okay, if we look at this carbon, watch. I'm going to use a red pen this time. You have one bond and then you have one going down like this. So this is the one that's two away. You have this bond and then you have this one. So it's going to be parallel to the two that I have in the red circles, like that. Okay, these ones are a little more complex. Okay, so let me erase some of this. Come on. There we go. Erase some of this junk that I have on here, which is lots of junk. Okay, so same thing here. This bond, right? You see how I drew that parallel to this one and this one, right? This bond is going to be, this bond is going to be going up like this. Why? Because it's drawn being parallel to this and this bond. And then I have one more. Use the red pen. It's going down like this. Why? Because it should be parallel to this line and this line. Okay, so that's how we draw the equatorial positions. But you notice, and I'll use a blue highlighter. Look at this. You have three hydrogens that are equatorial that are pointing up. It's actually, oops, that's not a blue highlighter. It's this one, and this one. And then you have three hydrogens that are equatorial that are pointing down. This one, and this one. So notice that they alternate up, down, up, down, up, down. Now, a picture is worth 1,000 words, but maybe a model is worth even more words than that. So let's go back to my model, and I'll demonstrate with my model. So, oops, there we go. So here's my cyclohexane. Here's the chair. Notice that you have 1, 2, 3 axial hydrogens that are pointing up. You have 1, 2, 3 axial hydrogens that are pointing down. Notice that they alternate up, down, up, down, up, and down. The same thing with the equatorial hydrogens. I have 3 that are pointing up. They're not pointing straight up, but you see how this is pointing up, right? This one is pointing down. This one is pointing up. This one is pointing down. This one is up and down. So they alternate up, down, up, down, up, down. So if you have a hydrogen that's up and axial, then the other proton is going to be down and equatorial. If you have a hydrogen that is down and axial, like this, then the other hydrogen is going to be up and equatorial. All right? Now that's going to take some studying in order to get used to all that. But you need to be able to go from the two-dimensional structure, right, to the chair in your mind. And then if you flip the chair, this is where it gets really spicy, okay? So look at this. I'm going to put a substituent here. We'll put this red atom sticking off of this hydrogen that's pointing up. So it's up and axial. Watch what happens when I change the conformation of the ring. When I flip it, it's still going to be pointing up with respect to the molecule, but it's not going to be axial. Watch. If I flip the bonds, now it's still up, but it's up, right? It's still going up. This bond is pointing up, but now it's up and equatorial. So when you change the conformation, and if you don't believe me, let me put something else. Let's put a methyl group, okay? If we have a methyl group like this, okay, it's up and equatorial. Watch what happens. If I flip the ring, now it's up and axial. All right, so that's what happens when we flip a ring. Everything still stays on the same side of the ring, but what was once axial becomes equatorial, and what was equatorial before will become axial. Let's say I have 2 axial substituents. Okay, I'll put this methyl, and this is actually an oxygen. The red is supposed to represent an oxygen, but you see how they're both axial? One's up and one's down. What's going to happen when I flip the ring? They're still up and down, but one is equatorial and they're both equatorial now. Okay, there we go. Let me go back to my screen here. Just give me a second. I lost you guys on my chat. There we go. Let's go back here. Let's get back in it. Here you go. So a lot to know about cyclohexane, and you have to be able to identify axial and equatorial positions, right? Every carbon has an axial position. Every carbon has an equatorial position. You've got to know how to draw all of the axial positions, and you've also got to be able to draw all of the equatorial positions. So you can spend a lot of time doing that. You also have to know the relationship between them, right? If you have a substituent that is up and axial, right? This is pointing up and it's axial. When you flip the ring, which is not a pancake flip, right? You don't put a pancake flipper in it and turn it upside down. You're actually rotating bonds. It's going to be up now, but it's going to be equatorial. Okay, so come on. Okay. All right, ring flipping, not like a pancake, occurs by the rotation of all carbon-carbon bonds in the ring. And I demonstrated that for you earlier today. Axial substituents become equatorial and vice versa. Equatorial substituents will become axial, as is shown right here. All right, this is where a model kit could probably come in really handy. Now, what if you had methyl cyclohexane? If I was to ask you, based off of what we learned in the first two lectures, or the last lecture, I guess, the first lecture on chapter 4, if I asked you, hey, you guys, could you draw methyl cyclohexane? And you drew this, I would have been like, 100%. That is methyl cyclohexane. There's nothing wrong with that at all. But notice that there are two possible conformations for methyl cyclohexane. We can have it where the methyl group is axial, and we can also have it where the methyl group is equatorial. But if you look at the distribution, you see that the equilibrium lies to the side where the methyl group is actually equatorial most of the time. And the reason why is because it alleviates unfavorable steric interactions that result when the methyl group is axial. Let me go back to my camera again, and I'll show you why. You can move on to the next slide if you want, but I think that the model is the best way to see it. So let's go back here to my molecule. If you were just thinking about it being flat on paper, right, if you drew it in 2D, this is my methyl cyclohexane, but we want to look at the chair, okay? So here's the chair like this. My methyl group is equatorial, like this. We said that it actually is in this conformation most of the time. Why? Because if you flip the ring like this, when it's axial, there's a problem. Let's look down this. If you look down, but what you see is you have what are called 1,3 diaxial interactions. So I'll try to demonstrate it like this. You see this hydrogen that's pointing straight up? These two here that are axial, it interacts with the methyl group. You see how they're kind of close to each other? And it creates some steric interactions, whereas when it's in the equatorial position, if you flip the ring, you don't have that interaction. The methyl group is far away from all the other protons. And that's why this conformation, where the methyl group is equatorial, is going to be preferred to the axial one where you have the 1,3 diaxial interactions. And if you're like, why do they call it 1,3? Because you have 1, 2, 3, 1, 2, 3. So they're, right, if you consider this carbon, they're 3 carbons away, and the hydrogens are pointing up like that. A 1,3 diaxial interaction. Now our book goes into, what if you have an even bigger substituent? If you change this methyl group to an ethyl, so now this is CH2, CH3, and you can probably guess where I'm going, right? The 1,3 diaxial interaction is even worse. Then look at it. Now this CH3 is right next to those two hydrogens, it's almost touching them. So that the bigger the group, the more it's going to want to be equatorial, like this. And it even shows you with the tert-butyl, it like almost doesn't exist. So let's go back to the old slides here. This is one of the things that I love about organic chemistry. It's not just looking at paper. You get to think, and everything's in 2D. It's interesting because you have things that are in 3 dimensions. You go back to 2 dimensions. And I find that something really enjoyable. So the steric strain from a substituent being in the axial position, we call that the 1,3 diaxial interaction. And this is what I was trying to show you. Right? And the reason they chose axial, if you're like, why didn't they put a methyl group there? It's because it can be anything that's big. Right? It could be an ethyl group, it could be an isopropyl group, whatever. But the 1,3 diaxial interaction is actually a gauche interaction, is all it is, really. And when you have the methyl group equatorial, it doesn't exist. Okay, you don't have the gauche interaction, right? This is a gauche interaction. We learned about that, what, half an hour ago? Okay, so really it's nothing more than a gauche interaction, is all it is. Anyhow, So the bigger the group, the more steric crowding, and the more it's going to want to be in the equatorial position. So if you go from, what does it say here? You've got a chlorine to a hydroxyl to a methyl to an ethyl to an isopropyl to a tert-butyl, right? This is methyl. This is an ethyl group. Excuse me. This is an isopropyl, and this is a tert-butyl. Look what happens in terms of the amount of axial to equatorial. Equatorial to axial ratio. Look, it keeps increasing. Then once you get up to a tert-butyl, I mean, it's, 10,000 to 1. I mean, so every 10,000 molecules, you're going to have one that's going to be in the axial position. If you're like, well, what would that look like? I'm tired of switching back and forth here between my camera, but this is why they pay me $3 an hour, is to show you stuff like this. Let me show you, just because it's fun to look at. So if you turn this into a tert-butyl, let me show you how crazy it is. Show you why it's 10,000 to 1. So here's a tert-butyl group. All right, so here's a tert-butyl group. I got to stand back here. That's a tert-butyl group when it's equatorial. Okay, you can see the cyclohexane here, and this is the tert-butyl group. Woo, all of this here. Look what happens when you flip the ring. Well, you're not supposed to break the ring, but when you flip the ring and you make it axial, here you go, like that. I mean, look at how nutty this is. There's no escape. Okay, it doesn't matter what, if this bond can rotate all it wants, but it's always right next to these two protons, right? If it's an isopropyl, you see, at least it can do this. It could be like this so that, the two methyl groups get as far away from the hydrogens as possible. Here they are close, but at least they can get away. Whereas when I'll put this methyl group back in, when you have the tert-butyl, there's no way to alleviate that strain. It's impossible. It can't be done because it's just always there. I could just sit here and look at this all day, but that wouldn't help us, would it? But kind of interesting. Give me a thumbs up if you think it's kind of interesting, or if you follow me, and if you have a question, of course, stop me, and we'll try to take a look at it again. And can these concepts be learned without me showing you a model? Absolutely, because you're supposed to be able to read a textbook and learn all the content from it. That's the purpose of a textbook. But the reason I always bring the models to class is because I'm the kind of person that likes to look at molecular models. I just find it a little easier, to look at molecular models and figure out what the heck is going on that way. All right. And again, you can buy a really cheap model kit from Amazon for probably a few bucks. I mean, in the syllabus, I mentioned the HGS model kits, which are pretty good. But really, you can have any kind of model kit, and it's going to get you where you want to go. Well, it's been about an hour now, so why don't we take a short break?